In this session, we will derive the wave equation from the Maxwell's equation. Again, we consider source-free situation. For current density J and the charge density rho is 0. And the Maxwell equations can be rewritten as curl E plus mu partial H over partial T is 0. And curl H minus epsilon partial E over partial T is 0. And we start from curl E. For this equation, we perform curl operation again. So we will have curl E plus mu partial over partial T curl H is 0. And now we have to expand this operation double curl. And let me remind you that for curl E, this can be expanded as gradient divergence E minus Laplacian E. So using this definition, we can expand this term in this way. We will have gradient divergence E minus Laplacian E and plus mu partial T. Here, curl H we can replaced by this term. We will have partial E over partial T is 0. Then let us rearrange this equation, and due to the rho is 0, so divergence E is 0 too, so we can only have these two items, and then we will have Laplacian E minus mu epsilon partial square E over partial T square is 0. Okay, following the same process, you can derive the wave equation for H and have Laplacian H minus mu epsilon partial square H partial T square is 0. These two equations are the wave equations for E and H respectively. And the wave equations, by its name, you can know that wave equation will help us to define the propagation of wave. Okay, so the solution of these wave equations should be a wave. And I believe that in your previous study, you have known the solution of the wave equation. That should be plane wave in this form. Amplitude vector A times exponential J omega T minus K dot R. This is so-called plane wave. The reason it is called plane wave is because light the phase front of this wave is a plane. Okay, what is phase front? Phase front are the surface formed by points with the same phase. Okay, so for wave with the phase front is a plane, we call it plane wave. Besides, the K here is defined as omega times square root of mu epsilon. As we have known the wave equation and its corresponding solutions, now we want to discuss the phase velocity. The phase velocity is the velocity of the phase form. So, according to the solution of the wave equation, that is the plane wave, the form of the plane wave is in this way. And the phase is defined here. So we will focus on a specified phase and to see how it moves with time. So we focus on a specified phase C1. We let omega t minus k dot r is C1. Suppose that at time t, the phase C1 is at position r, and at the time t plus delta t, the phase C1 move to r plus delta r. For both situations, the phase is fixed at C1. As a result, we can say that for this situation, we will have omega t minus k dot r is C1. For this situation, we will have omega t plus delta t minus k dot r plus delta r hat is also C1 because we consider a fixed phase, okay? And we can deal with these two equations and give us that omega times delta t will be equal to the absolute value of k vector times delta r. By the definition of the velocity, we will then have that the phase velocity, the velocity of C1 will be the displacement, the movement of delta r divided by the time interval delta t. And by this equation, the phase velocity will be equal to omega over the absolute value of k vector. Then finally, we can make a small conclusion that the phase velocity Vp is omega over k, and besides we know that k here is the wave number vector, or we can just call it wave number. Which is omega times square root of mu epsilon. Take this definition into here, you will know that phase velocity can be also expressed as the inverse of square root of mu epsilon. Okay? Besides, this one can be also written as mu epsilon 0 times square root of epsilon r. And for this term will be the the velocity of light wave in free space. And for this one will be the index n. Okay? So we can say that the phase velocity is omega over k, can be also expressed as the inverse of square root of mu epsilon. And also will be c over n, where n is the index of the material. Besides, the wave number k can also be expressed as 2 pi over lambda. Therefore, lambda can be also written as 2 pi over k. Okay? And from this equation, you know that the phase velocity can be obtained by the index. So the following table gives you the refractive index of material at a different frequency or at a different wavelength. For example, for SiO2, you will have different index at different wavelengths. So this means that the wave in SiO2 will have different phase velocity at different wavelengths.